Okay, today we'll talk about basic theory for the likelihood-based approach. So we'll focus on the theory with no missing data. The theory on the existence of missing data will be covered next week. We observe and observe data. So this is data, and this is an independent realization of random variable with density y, fy, and this density belongs to parametric family. So what do you mean by parametric? So it means that it's indexed by a parameter with a fixed dimension. So we later will allow n goes to infinity. I mean, we increase the n, but the dimension of the omega will still in p, are p and p fixed. Okay, and so that means the density is actually written as a for some zeta null, and zeta null is the true parameter. Okay, so likelihood function is nothing but a joint density function viewed as a zeta only. So that originally it's a function of y and zeta, right? So function of data and parameter, but we treat it as a given. So we are not going to vary y. We are not going to change y. It's fixed, but we will view it as a function of zeta. Okay. Maximum likelihood estimator is a maximizer of this likelihood function over the parameter space. So zeta hat is a actually function of y only, because you profile, you maximize it over zeta, so it doesn't depend on zeta anymore. Okay. By the way, this is should be omega, right? Sorry. Now, to discuss the consistency, one important condition is to make sure that model is identifiable. So model is identifiable, that means that the mapping as a function of zeta is 1-to-1. So that means you index your density, you index your model by zeta, but different zeta will imply different density, different distribution. Okay, and also when we talk about this density different distribution, we are talking about some difference on the set of non-zero measures. So we are not going to bother with a zero measure point. So because that does not make any difference at all for the probability in terms of the probability, right? Okay. Now, lemma 2.1 present important property of identifiable model. Okay. So one important, so that means, so what does that mean? M zeta is M zeta null, right? But see, this one is actually as a function of zeta. You can see that so y is a random variable, so that's we take a is integral, and so minus something that's a constant, actually doesn't depend on zeta, right? So then we call this, we define this q zeta, and so that means q zeta null. That this one is actually useful because what is q theta? Q theta is actually limit of what? Limit of theta. So this is, we can call it Qn theta. So the maximizer, by the way, what is the maximizer of this Qn theta? That's the MLE, right? Theta hat. Okay. So basically, at least if sample size n is large enough, then the maximizer of this Q theta is equal to Q null, right? So then that's good news, because what is Q null? Q null is Q0. Q0 is the true parameter that generates the data. So basically, maximizing this one makes sense, at least the largest sample size, because we know that in the end, if sample size is large enough, then the maximizer of this one is actually equivalent to theta null. But this is there's some tricky part, because Qn is a random variable, so there's some issue how to take care of the uncertainty. But the main idea is that this lemma shows that this is identifiable distribution. So important condition is that identifiable guarantees that this Q take the maximum at true parameter and it is unique. Okay. To prove this lemma, we need to use the famous Kullback-Leibler information with the two density function. So Kullback-Leibler information is essentially kind of distance, right? So this is, you can see that this is log of f y theta null theta 1, and then evaluate this quantity at the numerator part, not denominator. Okay, so that is the Kullback-Leibler distance information, and turns out that this is non-negative, and the equality, the minimum equality holds only when this ratio f1 and f0 are equal. Okay, with the property 1. So that's important information inequality, and the proof uses the Jensen's inequality. So Jensen's inequality, the graphical understanding of the Jensen's inequality is something like this, right? So you have a 2-point convex function. You have 2 point, and see the here you have x, and so a and b, and the point here is a kind of average, right? So you can think of random variable, and then so this point corresponds to g of expectation x, while this point is what? Expectation of g of x, right? So that justifies the this Jensen's inequality, at least graphically. And if it's strictly convex, then actually it's a constant with the property 1. And so we apply the information inequality uses the Jensen's inequality for this particular function. So for this particular function, okay, we should write it g. Sorry, because we already use g, right? So it should be g anyway. So then this one So this is definition, and this is Jensen, and this one, see, what's this? So this one is integral of f1 y, f0 y, f0 y dy. So it becomes 1. So the expectation is 1, and you take the log. So that's why you have a 0. Log of 0 is 0, right? Log of 1 is 0. So that that's 0. So that proves the non-negativeness of the Kullback-Leibler distance. And then the equality holds if the ratio, the random variable in G is a constant, so which is this one, right? Okay, so that gives the proof for the information inequality, and then we use this information inequality because m zeta is what? M zeta is zeta 0 f y zeta, so that is this one. And so that means that is f zeta 0 and zeta. Okay, so minus of the Kullback-Leibler distance. So we already showed that Kullback-Leibler is non-negative, right? So that means zeta is non-positive. I mean m zeta is non-positive. And with equality, if and only if these two densities are equal with the property 1, so that means this one, which means that m zeta has a maximum at zeta null. Okay. To show uniqueness, we can suppose we have another one equal to zeta, another one satisfying m zeta 1 equal to 0, then that means using the right. So this, that means you should have this one, right? So that means this one. So that implies zeta 1 equal to zeta 0 by the identifiability assumption. Okay.